Hi. Last lesson we looked at indefinite integrals and how we can actually integrate indefinite integrals when we have boundaries for A and B. And that led us into, well, we can start using this idea to help us work out, hey, an accurate answer area underneath a curve. So what we are doing today, for those people who are really excited like I am, is we're finding the area under a curve for the x-axis. We're going to be dealing with two types in this course, and a third type a little bit later between two functions. But this time we're just looking at the area under a curve and the x-axis itself, so sometimes above, sometimes below. So when we look at this, we've got a couple of examples up here on the board. We've got our first example in terms of an area between A and B, and we have the function which we're not sure of. We would know that if this area is above the x-axis, then we're going to get a positive answer. And we do take the upper bound and the lower bound, integrate it, and we get that actual answer. If, however, that area was below the x-axis, we get a negative answer. And we know that when we're calculating definite integrals, we have that part where we will have f of b minus f of a. But what happens here is that we could end up getting a double negative here. Way to get around that double negative is by using what we call absolute value functions. And what an absolute value function does is it just allows you to say that anything inside that, no matter what it is going to be a positive function. This works particularly well when it comes to integration, because this here, remember, is the area. And one thing that you really can't have is you can't have negative area. So if we wanted to add two different areas together, so if we had something that kind of looked like that, and we wanted to find out the total area underneath or with the curve in respect to x, and we had area 1 and area 2, well, this here is a negative area. So what we're going to get is we're going to get this plus minus this. And that means if we take this away, then that area doesn't exist anymore. But it must exist because area can't be negative. So to get around that, what we can do is we just take the absolute value of this. Even though this is negative, taking the absolute value turns it into a positive, so therefore I can actually add and get the entire area together. So, area underneath the curve uses the understanding of definite integrals. It helps us understand how to find that accurate area. We had the Riemann sums, or the upper and lower rectangles, which helped us find an estimate. This time we're going to get the actual area. Alright, it's an accurate result. So let's get into some examples. So the first example here is we've got find the area of the shaded region where y is equal to x squared plus 2. And we have bounds of 1 and 3. So, let's get into integrating this. First thing to do is let's put our integral symbol up there, our upper bound, our lower bound. Our function with respect to dx. Don't forget that dx is really important because it's telling you that you're integrating with respects of dx. Okay, so let's integrate. So we get x to the power of 3 over 3 plus 2x, all in the bound of 3 and 1. So therefore we get 3 cubed over 3 plus 2 times 3 minus 1 cubed over 3 plus 2 times 1. So let's see if we can do some maths here. 27 divided by 3 is 9. 9 plus is 15. We're going to minus from that. 1/3 plus 2 would give me 2n, 1/3 or 7/3. Yeah. So if we look at this properly, we're going to get 12n 2/3. So we get 12 and 2/3. Now, in the last one when we looked at calculating the definite integral, we didn't write the units. Because we're now finding area, we're saying that the area between 1 and 3 represents 12 2/3 units squared. So what we've done here is we've integrated like we normally did with definite integrals. However, the last part we knock on the units squared. Alright, let's have a look at a second example. And that second example is just up here. It's asking us to evaluate between pi and negative pi on cos x dx. So let's just sketch that up so we can have a look and see what it kind of looks like and what we're looking at here. Okay. We'll have negative pi on here. We'll have pi onto here. And we know that if it's cos x, it's going to have region of 1 up here. So let's just sketch this out. Alright. We're trying to find out this area. Okay? So we can do this two different ways. We're only going to do it one way, we're not going to do it two different ways. Alright? Let's work out the integral. So we know we're going to have the integral of pi on 2 and negative pi on 2 cos x dx. Alright, so let's integrate this out. We have sine x, yep, can we see that? Yep. Sine x in terms of pi on 2 and negative pi on 2. So again, you've got to remember your unit circle as you read through these. So therefore, we get sine pi on 2 minus sine negative pi on 2. Which then, if we look at this here, sine pi on 2. So sine pi on 2 is going to give me 1. Okay, so we're going to get 1. Okay, because y is 1, x is equal to 0. Minus sine on negative pi on 2. When we think about this here, we're going in the opposite direction. So if we're going in the opposite direction, we're going to get negative 1. So what do I mean by that here? Is we've started from this point. This here is pi on 2. So we've moved one 90-degree angle. If we wanted negative pi on 2, well, that's down here. We've moved negative pi on 2 from this part along. This is also 3 pi on 2, but because we're moving in that negative direction, we're going to get negative 1. And now we can solve this. 1 minus negative 1 is equal to 2 units squared. So what we've done here is we've worked out the integral using our trigonometry to solve the area between negative pi on 2 and pi on 2. And remembering our understandings of the unit circle. Let's do one last example and then I'll leave you to have some fun by yourself. So let's write this question up. So we've got function, I'm going to say this is 0 and m, and y is equal to the square root of x, and I have an area which is equal to 1 unit squared. Alright. This here is reversing everything. In the last couple of examples, what we did is we knew what these bounds were. We only know one bound now.